Hello, this is PHYS30141 electromagnetic radiation video number 6. In this video I'm going to talk to you about plane waves, by which I mean the coupling together of an electric and magnetic field to form an oscillatory wave which passes through either a vacuum or some medium. We start with Maxwell's equations. You should be familiar already with Maxwell's equations. They're given here on the top left. Switch to a laser pointer so you can see more clearly. And in a vacuum, what we are saying is that there are no charges or currents present, so therefore the divergence of the electric field is zero. The divergence of the magnetic field, of course, is always zero. And Ampere's law reduces to this slightly simpler form where there are no static currents. What we're aiming to do here is to arrive at a wave equation. And we can do that in a couple of steps. We apply a cross product to both sides of Faraday's equation, which gives the equation on the right-hand side. And we notice on the right-hand side that we can swap around the time derivative with the cross product. We then notice that the cross product, curl B, can be substituted in. We can apply Ampere's law, so we substitute that in to the right-hand side of this equation. We also note that we can apply a vector identity to curl E, and that gives us these two terms here, and we recognize that in a vacuum that del dot E equals 0. And what we're left with are two terms. We have del squared E and d by dt of dE by dt, and this is a wave equation. So what have we found here? We have found that the electric field in a vacuum has to satisfy an equation of this sort. And as a wave equation, we know that this is satisfied by functions which take the form f of x minus ct, where c is the velocity of that function. In other words, the function's shape remains the same, but its shape moves at some velocity c, where c here, of course, is 1 over the square root of this term on the right-hand side of the equation. I'll leave it as an exercise for you to find the equivalent equation for the magnetic field. This can also be obtained through a similar procedure to what we've just done for the electric field. And we can see that the electric field and the magnetic field separately must satisfy these two wave equations. We haven't yet coupled them together, but we will do shortly. A similar situation applies in media where there is a permittivity or a permeability. We note that in some dielectric non-conducting medium, we must replace the vacuum permittivity epsilon 0 with the value it takes in that material. So we have to multiply by an additional permittivity, a relative permittivity, epsilon. And the same thing is true for permeability, where I have to multiply the vacuum permeability by a relative permittivity, mu. This has an effect on the displacement and magnetic vectors, d and h, which are modified because of the relative permittivities. And we can describe the resultant electric fields and magnetic fields either in terms of the E and B values or in terms of D and H. But if we work through, we can arrive at similar wave equations. Here I show the one that applies for the electric field, where this velocity term in that wave equation has been modified by the relative permittivity and relative permeability. What does this mean? It means that the speed of that disturbance in that electric field is slower than it would be in a vacuum. It's slower because the relative permittivities and permeabilities are real valued, at least to start with. They're real valued and have values which are either 1 or bigger than 1. So therefore the denominator in this expression is larger than the vacuum situation, and I can describe the velocity as being equal to the speed of light divided by some factor. This factor, as we see here, is the square root of the product of the relative and permittivities and permeabilities, and we see immediately that the permittivity, which is the polarization response of a material to an electric field, is related to the refractive index. We of course here are talking about the passage of light through a medium, and by describing it in terms of this permittivity response, Maxwell's equations has shown us that there is a coupling together of the electrical and optical behavior of material. The refractive index n is equal to the square root of the product of the relative permittivity and the relative permeability. Now, this is not the full story. We have implicitly assumed in our description of a real dielectric material that the response of the electrons in this material, this is what's giving rise to the polarization of that material and is also what is giving rise to the permittivity. We're assuming that response does not depend on either the amplitude of the electric field or on the disturbances which have happened before. Neither of those things is strictly true. We are implicitly assuming in this derivation that we have a linear response of the material, of those electrons, to a passing electric field. We are also assuming that the same thing is true for the permeability. Both these values should be thought about as being functions of frequency, and in addition, the relative permeability in most real materials is about 1. So some things to watch out for in textbooks is quite often the relative permittivity will disappear from expressions because its value is very, very often 1. And you should also watch out for different notation where sometimes the relative permittivity is given with a subscript r and sometimes it isn't. So be careful when looking at these derivations that you're correctly accounting for whether the epsilon 0 or the mu 0 are appearing or not. Now let's think about plane waves. Again, we're thinking about this wave equation, this wave equation for the electric field and the magnetic field that we've obtained for the in-vacuum case, where the velocity of some disturbance is equal to c. And we're going to look at the special case where this disturbance, this arbitrary function f, is only moving in the z direction. So I'm considering forms of the electric field which have the form E of x is a function of z and t only. It has no variation in the x or y direction. And we have an electric field that points in the y direction, but is again only a function of z and t. And when del dot E equals 0, this gives us that Ez must be equal to 0. This is our description of a plane wave moving in the z direction. And as we said, the wave equation for the electric field is satisfied by two basic kinds of solution: an arbitrary function f of z minus ct, or an arbitrary function, here denoted g, of z plus ct, where z minus ct denotes a wave moving to the right in the positive z direction, and z plus ct denotes a wave moving to the left. Now this is an arbitrary function we're talking about, and we can decompose that arbitrary function into separate frequency components. If I do that, each frequency component has some frequency omega, and it will have a corresponding wavelength k, where the peaks and troughs in the electric field occur at some separation lambda, the wavelength, where lambda is 2 pi over k. Now, in our decomposition of this electric field into these frequency components, k is being thought of at the moment as a real valued scalar quantity. I note here that it is not always a real valued quantity. We will look at absorption later on, and here we'll look at it as a scalar, but it will later be describable as a vector. Now, the frequency component omega with a wavelength k is relatable to the velocity of the wave c via the dispersion relation. This dispersion relation, as it's called, at the moment is quite simple. Regardless of the frequency, the wavelength is the same. That is because the permittivity is not varying with frequency, and neither is the neither the permittivity or the permeability are varying, and therefore the velocity of the wave is independent of frequency. So the different frequency components stay together, so there is no dispersion of those frequency components. There's no spreading apart of them. So this dispersion relation is very simple. There is a single speed for all the different frequencies. Okay, so our dispersion relation is omega divided by the modulus, the size of k. Now, how are the electric fields and the magnetic field related to each other? So here is our plane wave one more time. So our plane wave in its general form can have either an electric field in the x direction or an electric field in the y direction, or added together in some linear combination. And because they both satisfy this wave equation in the x direction and the y direction, both components in x and y move at the same velocity. They have general solutions f of z minus t ct or g of z plus ct. And I can describe individual frequencies in the way that I've just shown here. E equals E0, e to the I omega t plus or minus kz, where E0 is the amplitude of that wave. How is that related to the magnetic field? Well, I go back to Maxwell's equations, and straight away I can see that the curl of E is dependent on the time variation of B. So I take dB by dt and I express that. Remember that there's going to be a magnetic field which also satisfies Maxwell's equations, which has the same form as this electric field. It satisfies this wave equation. So it will have the same frequency dependence for that frequency component. When I differentiate it, I get I omega appearing in the front. And when I take the cross product of the electric field, I see these two terms appearing. There are only terms in the x direction and the y direction. And when I identify and I relate the amplitude of the magnetic field in the x direction, it can be related to the magnitude of the electric field in the y direction. And just by inspection, I can see that the magnetic field is proportional to the electric field in both directions, but with a scaling factor k over omega. And of course, k over omega is simply 1 over c. So immediately you see that the magnetic field is c times smaller than the electric field for any plane wave solution in a vacuum. Now, this is for the special case of a plane wave moving only in the z direction, but I can generalize this statement, and if I consider a plane wave moving in any direction z, I can where I can rotate my axes from what I've just shown to any arbitrary direction. The electric field, which is of course here transverse to z, can be related to the magnetic field direction, and you see here that the magnetic field is now perpendicular to the electric field and scaled in magnitude by this value k over omega. Now, if I look at those components directly, and I can write down the dot product between the electric field and the magnetic field, and as you would imagine, when I add together those components, the dot product of those two fields is equal to 0, as I might expect. Therefore, the electric field is perpendicular to the magnetic field. So to summarize, in a plane wave, I can separately show that the electric field and the magnetic field satisfy a wave equation. However, the electric field and the magnetic fields are coupled together via Faraday's law in such a way that the electric field is perpendicular to the magnetic field, and moreover, the magnetic field is a value c times smaller than the electric field. Now, in the general case, where the plane wave can be moving in any particular direction, I can talk about that in terms of the wave vector k. So k, the direction of k describes the direction in which the wave is moving, and k dot r describes the number of wavelengths which have occurred between the origin and the location R. So the electric field can be described in general terms for a plane wave at some distance r in terms of an amplitude of the electric field transverse to the direction of propagation of the wave. And again, the magnetic field can be related to the electric field by taking the cross product with the wave direction. And I can express that in one of two ways. I can either normalize the k vector and then divide by the speed, or I can keep the magnitude of the wave vector in the direction of k, and I simply divide by omega. And you'll see both these descriptions used in textbooks. Now let's look at some special cases of these plane wave solutions to illustrate how they might look. So again, I go back to a plane wave moving in the z direction. So this plane wave moving in the z direction has only components in the ex and ey directions, in the x and y directions, which have some amplitude E1 and E2, say. And in general, they will have some oscillation which can be described in terms of two phases, phi1 and phi2. Straight away, I can, without loss of generality, only include phi2, which I now label as phi, and I cross out phi1. So I can describe my plane wave solution, E, as a vector where the electric field strength in the x direction is E1 cos omega t, in the y direction is E2 cos omega t plus phi. And this is the general solution for a plane wave moving in the z direction. And again, for whatever the solution is for E, B can be related to E by taking the cross product. So B always points at right angles to E at any given instant. So some particular cases of this, let's imagine that phi is equal to 0. Then we have E1 and E2 both oscillate together. They are in phase. We have a common time variation cos omega t, and this is linear polarization. So when viewed along Z, the electric field at any particular instant moves backwards and forwards along the line formed by that vector E1, E2 in the xy plane. So each one of these components is oscillating backwards and forwards, but they are oscillating together in phase. So in this plot, I show only the E2 component, which would be the only component if E1 was equal to 0. And you can, of course, see that I can rotate the axes x and y in order to make either E1 or E2 equal to 0. A different situation is when I have circular polarization. Now there is a phase shift between the oscillations of E1 and E2. At the point in time when the electric field in the x direction is maximal, circular polarization states that the electric field in the y direction is at a minimum, at 0. So when phi is equal to 90 degrees, either plus or minus, the electric field will rotate in the xy plane as a function of time. So in this plot, I'm looking at a particular value of z, and the electric field vector is rotating as a function of time, and in this case it is anti-clockwise. This is known as left-handed circular polarization, when the phase shift between the x and the y electric fields is minus pi/2, minus 90 degrees. And if I were to look at a fixed time but vary z, I would see this vector of the electric field, as I varied z, that would vary in the opposite direction. For right-hand circular polarization, the phase shift is plus 90 degrees, and in both cases I have that the electric field in the x and the y directions are equal to each other, and in this case, of course, the electric field vector now rotates as a function of time in the clockwise direction. That's why it's known as right-handed, and the other one is known as left-handed. So together, linear and circular polarization are two special cases of of the way in which the two electric field vectors can move with respect to each other. A more general case is elliptical polarization, where as well as there being some phase shift, there may also be a difference between the magnitude of the vectors E1 and E2, and now the point of that electric field vector will move in an elliptical form, and that will be somewhere between the circular polarization case and the linear polarization case. Now, in real visible light situations or real electromagnetic propagation situations, we can also have the situation where this electric field vector moves randomly. We can have a random polarization where we have an effectively random motion or a random variation of E1 and E2 as a function of time. Now let's think about the energy which is carried by these electromagnetic waves. So what have we done so far? We have described that plane wave solutions of Maxwell's equations can be given in terms of an electric field which has some time variation and some spatial variation, and a magnetic field which has some time variation and spatial variation, and the magnetic and electric fields are coupled together and they have a ratio of strengths. And by having this minus sign, we are describing electromagnetic waves which are moving in the positive z direction. But of course we already know that an electric field present in a particular location gives rise to an energy density in that location. So clearly, as the electric field grows and shrinks at a particular location, the energy density at that location also grows and shrinks, and the same can be said for the magnetic field. So if I look at these plots on the right-hand side, I imagine this is a situation at a fixed time. As I look along Z, the places where the electric field is a maximum is where the energy density is highest. And of course this has a cos squared form because the energy is a positive definite quantity. And if I look closely at the magnetic field, you will see that in the plane wave solution, the places where the magnetic field is a maximum are also the places where the electric field is a maximum. The energy in the electric field and the magnetic field move up and down together. Just to point out that that's a B0 squared there. So as time changes, these maxima in the energy move to the right. So clearly energy is moving in this electromagnetic field. The energy is moving along with the wave. It must be moving at c. How much energy is present in the electric and magnetic field components? The electric field component is E naught is equal to epsilon naught E naught squared cos squared omega t minus kz. And if we relate the magnetic field strength to the electric field strength, we can show that the magnetic field energy density is equal to the electric field energy density. That's an important statement. It says that in an electromagnetic wave, equal energy is carried in the magnetic field as in the electric field. So therefore, I can describe the total amount of energy in my electromagnetic wave simply by having twice the electric field quantity. So I simply remove this half term, and this is the energy density. If I average over time, or equivalently over distance, I can show that the energy density on average through these peaks and troughs is equal to some scaling value times the square of the RMS value of the electric field. So you can express this energy density in a variety of ways. Watch out for these factors of 2. So the RMS electric field is equal to the peak electric field divided by the square root of 2. How do we relate that to our previous definition of the Poynting vector? In our earlier discussions, the Poynting vector was defined in terms of the cross product of the electric field and the magnetic field. And now we can see that the Poynting vector points in the direction of the flow of the electromagnetic wave, in the direction that it's propagating, and it moves in the direction of the energy flow. And if I calculate this for our plane wave solution, I can calculate explicitly the magnitude of the Poynting vector in terms of the peak electric and magnetic fields, and I can show that the Poynting vector also has a cos-squared variation with time and position. I can now calculate the average value of the Poynting vector directly by looking at the electric and magnetic fields. And it has this form, where I have a factor half appearing because of the averaging of the cos-squared term. And I can rewrite this by substituting in for the magnetic field, because I know the magnetic field is c times smaller than the electric field. So this is 1 over c here. So I can rewrite the Poynting vector in terms of the electric field only. Now, of course, this term on the right is just the energy density. And if I inspect these factors, I can say that the Poynting vector is equal to c times the energy density. So what does that say? It says that the amount of energy passing through a plane as a per unit time is equal to the energy density in the wave. So the amount of energy that passes through some plane is equal to the amount of energy in some volume upstream of that times the velocity of that wave. And of course that makes sense.